Um, Hello, can you hear me? All right, so let us start. Continue with the discussion of the perturbations. So let me just remind you what where we stopped yesterday. So we were talking about the linear perturbation theory in FRW cosmology, and we consider two qualitatively different regimes, which we call subhorizon and superhorizon. So there was superhorizon regime when so we went to the Fourier space or the momentum space, and then we defined a co-moving Hubble, and superhorizon was defined by k over the co-moving Hubble to be much less than 1. And then there was the subhorizon regime. Where k over h is much larger than 1. So what we saw was that in the superhorizon regime, we have perturbations which are so first of all, yes, so here we saw that there are, in superhorizon regime, we normally have solutions which are constant, time independent, or we have decay and growing solutions. But for instance, for the equation that for the field that we were considering, the growing mode was actually constant. While here in the subhorizon regime, we have oscillating. Solutions. And moreover, what we saw was that when W is larger than minus a third, the different momentum modes, they start superhorizon, and go subhorizon and oscillate. So here, modes. When things go from superhorizon to subhorizon, we normally say that modes enter the horizon. So and oscillate. While when W is less than minus a third, or in other words, in the inflationary phase, the opposite happens. Modes go from being subhorizon to superhorizon. So therefore, they exit the horizon. And freeze. So there's this very crucial qualitative difference between these two regimes, and that's how inflation sets the initial condition for the perturbations in later cosmology, because during inflation, modes exit the horizon and then they freeze, and then they become the seeds for the later perturbations that we are interested. So what I'm going to do now is I'm going to focus on the perturbations of a scalar field, a massless scalar field that lives on de Sitter. So de Sitter for us was an approximation to inflation. We later make this approximation more precise or take it into account. So we want to first focus on the perturbations of a single scalar field on de Sitter. At this moment, I'm not talking about fluctuations of the metric. You can imagine that we are doing field theory on curved spacetime, but without any dynamical metric. So the action that we were, So therefore, we have massless free field in the center. So again, the action we wrote it yesterday, I repeat it here, is so let me write it directly in conformal time. So it is d eta d3x times a to the fourth, a squared times phi prime squared minus grad phi squared. And since we are in the theta, so we know that the scale factor A is e to the ht. That tells us that it is equal to, so we can solve for the conformal time and get A to be equal to 1 over h. This h is h during inflation, so what I was calling hi. Let me not call it hi. So this for this lecture, whenever I say h, is h during inflation. So it's going to be minus 1 over h eta. And there is a factor of 1/2 here. So what do we do with this? Again, what we did was that we looked at the equations of motion in the momentum space. So we wrote phi of eta and x to be integral d3x e to the I k dot x times phi k of eta. And then we saw that this phi k of eta satisfies the following equation of motion. It was phi double prime plus 2 curly h phi plus k squared phi. But curly h phi, curly h in during inflation is, so what is it? It's just minus 1 over eta because it is a prime over a, and a goes as 1 over eta, prime is d by d eta, so this is just minus 1 over eta. So we get phi double prime minus 2 over eta phi prime of k plus k squared phi k is equal to 0, where k squared is just modulus square of this vector k, the momentum vector. So what is the plan? We want to find the solutions to this equation. And then we want to quantize this field by expanding it in terms of creation annihilation operator. We want to choose the right vacuum of this theory. And with that choice of the vacuum, we want to determine what would be the correlation functions of phi at the end of inflation. So the problem is, so the route that we are following is more or less similar to what we do when we quantize a harmonic oscillator. There we find the solutions for the harmonic oscillator. There are e to the I omega t and e to the minus I omega t. We then expand the field, expand x in terms of creation annihilation operators. We have the vacuum that is annihilated by the annihilation operator, and then from there we can calculate the correlation function. So this is, we are following a similar route here, except that instead of one harmonic oscillator, we have now a collection of them. you can think of any of these K modes as being something like a harmonic oscillator, except that it's not exactly a harmonic oscillator because we have this extra term here. So if it wasn't there, it would be a harmonic oscillator. With omega the same as K. All right, so we find the solutions of this equation. I call the solutions by F. So the solution is a second order differential equation, so there are two solutions. One of them is the one that I'm going to write, some constant that we are going to determine soon, plus I k eta times e to the minus I k 8. And the other one is just the complex conjugate of this. So the other one is fk, the star of 8. So now why do I call this a positive frequency solution? It's because as we go to early times, it means that so eta, during inflation, eta goes from minus infinity or some very large negative number which corresponds to the beginning of the inflation up to 0. So if you are in excited sitter, eta goes from minus infinity to 0. That would be the end. This is eta equals 0. So early times corresponds to large negative values of eta. So what happens there? When we go to early times, to very large and negative values of eta, the modes, so remember what happens to the modes is that we are in this phase, omega w less than minus etc. When we go to early times, the modes are deep inside the horizon, and they are oscillating. So for instance, here you can see if I go to large eta, this term is negligible, and we just get oscillating solution as the dominant behavior. So we have the oscillating modes. These oscillating modes, we can, for them, we can choose the vacuum by using the same logic as we use to choose the vacuum when we talk about the field theory in Minkowski space, because the frequency of the modes is much larger than the expansion rate of the union. So at very early times, this is the mode that is analogous to e to the minus I omega t, the modes that go as e to the minus I omega t when we talk about the field theory in Minkowski space. So we choose the vacuum, and vacuum would be the state that is annihilated by the annihilation operator. So we choose the vacuum to be such that the coefficient of this positive frequency mode annihilates it. So the annihilation operator would multiply fk of eta. And then I have fa minus k dagger well, actually, f only depends on the magnitude of k, so I don't need to put a vector sign here. So here I just remove the vector. So that's what the is there air conditioning here? There? Oh. Is it on? No. All right. So what did I do? I had my free field, my oscillator. I find the solutions of the oscillators. There are two solutions. There's one of them that at early times oscillates with positive frequency. Positive frequency means that it goes at e to the minus I omega t. The annihilation operator would be multiplying that mode that has this behavior. And this is so this is basically when I say this is I'm essentially choosing the vacuum to be the state in which if I go deep inside the horizon, I see the usual Minkowski vacuum. So once I do that, then the next thing to do is to fix the coefficient C here. Once we determine C, then you can see that we know essentially everything. Because what happens is that these solutions that we are finding, they're oscillating at early times. But as I send eta to 0, go to the end of the inflation, these modes stop oscillating. They just asymptote to some constant value. And that constant value is very important. It's exactly what we are looking for. Because, so imagine we want to ask about the correlation function of phi of k at some eta. Let me call it eta r. And eta r means some late time slice here. That corresponds to the reheating. So of course we don't, in reality we don't want this near de Sitter phase to continue forever. We want to end it and have reheating. So that means that this de Sitter space has to be cut at some eta r. So we want to look for the 2-point function of this momentum modes. Well, of course, we could ask the question about the 2-point function of the fields in position space, but then, as Raoul explained, we can go to the Fourier space. So this is a kind of question that we are interested in asking. 2-point function, the expectation value of the fluctuations of these fields for two momenta. And what we are going to get is that, so this, another property of this creation annihilation operator is that they commute to 1. Or since we have a continuum of the k modes, we have AK dagger prime equals 2 pi cube delta 3 of k minus k prime. Now, if we plug this expression in here and use that commutation relation, what we are going to get is 2 pi cube delta 3 of k1 minus, actually k1 plus k2, because in phi k we have a dagger of minus k, times this fk of eta r, the norm squared of fk of eta r, which is equal to, so we have phi k of eta r, and phi k1 and phi k2. And now if I plug this expression in there, what we are going to get is c squared times 1 plus k squared eta r squared. Now, if this eta r time slice is late enough so that the mode that I'm interested in is super horizon at that time, and super horizon means that k over h is much less than 1, which means that k eta squared is much less than 1. So if I take a k over h r to be much less than 1, which is equivalent to saying k eta r is much less than 1, then this term is negligible, and we get just c squared. So the expectation value of the fluctuations of this field at late times is determined by the normalization of these modes. So if we determine that, then we know what is this expectation value, and then this will be useful for us, because then we are going to relate it to the cosmological fluctuations. Is there any questions so far? Yeah.
The norm will change when you cross the horizon.
The norm, you mean C?
The
You mean C?
Yeah.
So the question was that if C changes when the modes cross the horizon. The answer is no, C doesn't change. C is just a constant here. This is the full solution. This expression is the solution of this equation. And of course, I can multiply by any constant because I have a homogeneous equation. So any constant times this is also a solution. You can see from here what happens when modes cross the horizon. When k eta, the absolute value of k eta is very large, what these modes are doing is that they are oscillating. When the absolute value of k eta becomes much less than 1, then actually let's do that because that is a useful exercise. So we have fk of eta, and we want to see what happens. So let's consider the two regimes, right? If I go to the sub-horizon case, when absolute value of k eta is very large, I can forget about this 1 factor. Then it becomes just I c k eta e to the minus I k eta. This is the oscillatory behavior that I'm talking about. This is the one that we are expecting from modes that live in Minkowski space. They have the property, they have a phase, oscillating phase that goes at e to the minus I omega t. So if you are an observer who lives there during inflation and who measures modes which are deeply inside the horizon, that observer wouldn't know that he lives in the city. Like we live in the city, right? But we do experiments at LHC, and to make predictions for those experiments in LHC, what we use, for instance, this QFT textbooks. They are all written about, they all discuss field theory in Minkowski space. So in order to make predictions for the experiments that we do on Earth, we use field theory in Minkowski space because the time scale of variations, cosmological time scales, is much, much longer than the frequency and energy scales of the modes that we are dealing with in our everyday life experiments at LHC. So it's exactly the same logic applied to this problem. If I'm someone who lives during inflation, and I'm measuring things at very small scales, I would expect that most of the times I should get vacuum, the vacuum that I expect from my QFT book, like from Pesky and Schroeder. I open, there is a vacuum that says, the Minkowski vacuum is written as, in which when I write fields, I write annihilation operators times the mode that goes at e to the minus I omega t. Now this is the mode that is equivalent to the modes that we would call e to the minus I omega t. Why? Because if I take the time derivative of the phase, so what is omega? Omega is just d by dt of k eta, and that is that d by dt of k eta is exactly k over a. So it's the physical frequency of the mode that I measure. So this is the early time behavior of the modes. They are exactly the same as, not exactly, but they are adiabatically changing with time. But for very short time scales, they are the same as the modes in Minkowski. Now at late times, so this was when k eta is much larger than 1. When k eta is going to 0, then the behavior changes qualitatively, because now, if I set k eta to 0 here, I just get C. If you like, I can expand it a little bit more. So we get C times 1 minus maybe 1/2 k eta squared plus or minus I times I over 3 k cube eta cube. These coefficients might not be exactly correct, but something like that. We can just expand in k eta at late times. And so you see that the leading behavior is just a constant. And that's what happens. At early times it oscillates, at late times it goes outside the horizon and becomes a constant. That's the qualitative behavior that we were expecting before. Okay, so now how did we choose the vacuum? We chose the vacuum at early times, using just the usual logic that we use in everyday life when we do experiments. And that was the choice. I multiply, the vacuum is the state that is annihilated by these A's, and A's multiply the modes that have this behavior, this oscillatory behavior. And then we see that at late times, these F modes go to a constant. This constant is the C, and that determines the expectation value of the superhorizon. So we want to determine C, and the way to determine C is to, of course, we haven't finished quantizing this. We want to do the quantization of the field. We should make sure that the quantum field and its conjugate momentum have the right commutator. And getting the right commutator fixes this C. So therefore, let us determine the commutator. Let us determine the momentum. So if I ask about P of eta and x, the way we determine it is that we take the action with respect to phi prime of eta and x. And this is going to give us what? 1 over, gives us phi prime over h, h squared, eta squared, right? Phi prime of eta and x. Now phi prime, once we write the field like that, once we expand the field like this, then we can also easily determine phi prime. So phi prime of eta and x is equal to integral. So the phi field has been expanded in terms of this Fourier mode. So here I get d3k e to the I k dot x. Sorry, let me just directly write pi. So we have this factor h squared, eta squared. We have ak f prime k of eta plus a of minus k dagger f star prime k of eta. And then we can use this commutator of the annihilation and creation operators to calculate phi of eta and x and pi of eta and x prime. And we want to demand that C is determined such that this commutator is equal to I times delta 3 of x minus x prime. Right, so this is the right canonical commutation relation. And this is the relation that is going to fix this normalization C for us. Why? Because this, so if I use this commutation relation between A's and A daggers, what I'm going to get is integral d3k e to the I k dot x minus x prime times, so I'm going to get f of k eta times f star of k eta prime minus f star of k eta times f prime of k eta. Okay, so what is this? So f prime of, I guess I write here, f prime of k eta is equal to c k squared eta e to the minus I k eta. Therefore, fk of eta times fk star prime of eta is equal to c squared k squared eta times 1 minus I k eta 1 plus I k eta. And this difference is just twice the imaginary part of that expression. Sorry, I missed something because there was a factor 1 over h squared, eta squared here in the differential momentum. So twice, so at the end of the day, how are we going to get I times delta 3 of x minus x prime if this whole expression evaluates to I? Then that integral is just the Fourier transform of a delta function. So what we want is that 1 over h squared eta squared times twice imaginary part of fk of eta, fk star prime of eta is equal to 1. Which tells us that, so what is this equation? It is twice c squared. The imaginary part is k cubed times eta squared cancels. I get k cubed divided by h squared equals 1. So c squared is equal to h squared over twice k cubed. So therefore, if I take k eta r to be much less than 1, this two-point function of the free field that we are talking about is going to be, c squared, which is h squared over twice k cubed. Any questions so far? So as you see, so we were talking about these momentum modes. And these momentum modes were happily oscillating when they were inside the horizon. Nothing very special about them. Now we see that something, the dramatic change happens when they go outside the horizon. The two-point correlation function just goes to this constant value. So what we are going to do next is to apply these results to the actual fluctuations during inflation, which means that we want to now think about having this inflaton field and then the dynamical metric take into account the fact that now that there are fluctuations also in the metric. So we want to put everything together but use this result. But this is already an indication of what we are going to get at the end of the day. which is that we are going to define some gauge invariant set of observables, which are made out of combinations of these metric fluctuations and inflaton fluctuations. And then those gauge invariant fluctuations are going to have a two-point correlation function that is given by an expression like this. Yes?
How do you know that the relating time is just a short period after the end of inflation? Like, how do you know that the energy density is going to decay fast?
Okay, so the question is that how do I know that the reheating period is short? Or the transition, the decay from the inflation into the hot phase is faster. Actually, I didn't make that assumption. You could even imagine that we are exactly in the center, right? So this eta r didn't have to be the time at which inflation ends. It didn't have to end. You could just decide that you want to measure this two-point correlation function at that time eta r. Inflation could continue afterward. The point is that if k eta r is much smaller than 1, right, which means that if the modes that you are interested in at that time is super horizon, then the two-point function is given by this expression plus corrections which are very small. So to derive this, I have not made any assumption about efficiency of reheating process. Yes?
What about the phase of C? Because we found that its absolute value should be given by this. Take that limit, but what about the phase at this number? Because when you superpose all the modes are quantized field, couldn't this be important?
Couldn't the phase of C be important? Let's see. So if we go to very early times, right? So then we can even consider when we do field theory in Minkowski space. The phase that we choose is not that significant because it corresponds to a shift of the time, right? So yeah, I don't think it matters. You can just redefine the phase. All right. No questions? Are you sure? Okay, so now we want to go to the real problem. So how do we go to the real problem? So this phi here for me was just a massless scalar field living on the Ceter space. But of course, at the back of my mind, I had the case of inflaton. If we consider, so we said that our models of inflation were made of a scalar field with action d phi squared minus d phi squared minus v of phi, and it has a small mass, this field. So if we consider the fluctuations of this inflaton field, And if we ignore the potential, so if we wrote phi to be some phi bar, the background plus fluctuations that I wrote it with this curly phi. And if I assume that the potential is exactly flat, then the problem for these phi fluctuations would be identical to what we had done here, right? If the potential for inflaton was exactly flat, then fluctuations of inflaton would be just the massless free field in living in the center. However, we saw that this potential is not exactly flat. It has to have some v prime during inflation. So we are really talking about a potential like this. And so also if I look at the theory for the perturbations, if I do this decomposition and write the action for this curly phi, now it won't be exactly a massless field. There will be some mass of this phi which will be proportional to v double prime. So there would be m squared of phi, which is v double prime evaluated at phi bar. So it's not a massless field, and if you have a massive field, then this analysis would change. In particular, when modes go outside the horizon, if they have some small mass, they don't remain constant; they change in time. Which also can also be seen from this picture. When modes go outside the horizon, they can be thought of as being just uniform, homogeneous solutions, and we know that the homogeneous solutions roll down. We have this slow roll solution. So then you can ask, why should this result have anything to do with what we observed today? If these fluctuations that I was deriving, if the inflaton fluctuations are going to be time dependent outside the horizon. If things do not freeze outside the horizon, then we cannot be sure what we see today is related to what was happening during inflation. We want something to be conserved outside the horizon, and therefore to be independent of the details of reheating, whether they happen fast or slow, or what mechanism derived in that reheating phase. So the way these fluctuations of the inflaton field are actually going to lead to those conserved fluctuations, it's something that we can be worked out in detail. The essential idea is that the inflaton field acts as a clock. So you remember that the inflation we wanted to end. So let's say if we consider m squared phi squared model. Then there will be a time at which inflation ends. And if this field happens to have some jumps, quantum jumps, those fluctuations, that would mean that the inflation would end at different points at different times. And if this different, so essentially we are talking about the inflaton field. Which works as a clock. So we have this clock. However, the clock is not super precise because it has these fluctuations. And these fluctuations means that this time of end of the inflation is going to be different at different points. And this is the fact that eventually leads to production of perturbations that we call them adiabatic perturbations, which are conserved outside of the horizon. Now, in order to do it precisely, of course, we should take into account the metric fluctuations and then work a little bit harder. And I am not going to go through the full analysis to derive that, but I'm going to give some arguments and then give you the final result for the quantity that is actually conserved and is the thing that is going to be related to the, for instance, CMB fluctuations that we are going to see. So therefore, now we want to discuss the full problem. And we have inflaton and we have the metric, both of them can fluctuate. So how do we do that? Of course, when we have gravity, then we have gauge symmetry, so diffeomorphisms. We have to somehow fix those diffeomorphisms to be able to solve the problem. And there are various ways to do that. The way that I'm going to describe it here is not the first method that was used. I think the first method was, the first correct way of doing it was done by Mukhanov. But the way that I'm going to explain it is I'm more or less going to follow the way that it is explained in the paper by Maldacena. I add the reference in the website, which to me seems to be the most direct way of getting the answer. Still, I'm not going through the details. So we want to fix the gauge. Let us first use some parametrization of the metric. So we are going to write the metric, but now it's per term. So before we had just the de Sitter metric on per term, or FRW on per term FRW. Now that it is per term, we have to include a lot of new fields in here. So I will have minus n squared dt. I use something that is called ADM decomposition of the metric. Where Hij is a squared. So this is just the background. A squared is just a background scale factor, just a function of time. But then the fluctuations are encoded in this variable zeta, which describes the scalar fluctuations. And then the tensor fluctuations gamma ij, where this gamma ij is traceless and transverse. So these two are gauge choices. I have used some of the gauge freedom to set trace and the divergence of gamma ij to 0. Now, what about the phi field? So remember, what we start with is what? We have an action that is the action who has two fields in it. There is G mu nu, the metric, and the inflaton phi. And then it is made of two pieces. There is the Einstein-Hilbert action What's the action for the phi field, which is just a kinetic term plus a potential? So the fields that we have is a scalar field plus a metric. And now I'm choosing, I'm making gauge choices. So far I fixed part of the gauge symmetries that I have. I actually, here I have fully fixed spatial diffeomorphisms by these choices. However, there is also time diffeomorphism, and the time diffeomorphisms are fixed by choosing phi to be just phi of t. So I choose the field to be completely unperturbed. How can I do that? Let us, so this is essentially a choice of time slices. So I'm choosing my time slices. I'm slightly perturbing my time slices so that on every time slice, the value of field phi is constant. So I'm taking full advantage of the fact that phi field is going to act like a clock for me that tells me when the inflation ends. Now, why can I do this? In general, I wouldn't be able to do that if phi didn't have some time dependence on the background. But since it does have a time dependence, I can always make this choice. So imagine before we had some, we were choosing some other time coordinate, say a time coordinate in which this zeta parameter is 0. Now we want to see how we can go from that time choice, a choice of time slices, to the other one in which phi is constant. So we say that t is going to be this time variable is going to be the original one. So let me call it, so there is a t tilde in which when I have phi of t tilde and x, which is equal to phi bar of t tilde plus fluctuations. So I want to take t to be t tilde plus some delta t. And then I want to require that phi of t and x is equal to phi bar of t tilde. I want phi of t and x to be independent of the position, to be uniform. So if I can plug this in here, so it tells me that phi of t plus t tilde plus delta t, let me call this also delta t tilde because it appears on this side of the equation, is equal to phi bar. Now how do I write that? I use this expression. I know that phi of t tilde is fluctuating. So I have two terms here at linear order in fluctuations. One of them is just phi bar of t tilde plus delta t tilde plus phi of t tilde plus delta t tilde and x. So the goal is I want to show you that there is a choice of this delta t tilde that I can make so that this condition is satisfied. This condition is the statement that the surfaces of constant t are surfaces of constant phi. So can I satisfy this? Yes, I can, because let us just linearize in delta t and phi. We are doing a linear analysis. So this part is just linear. Of course, if phi is just curly phi is 0, that is the slices that we are looking for. So therefore, this delta t that we are looking for, it should be at least should be of order of the phi, of order of the perturbation. Therefore, here in this part, I can neglect it. So I'm working at order phi. So on the left-hand side, what I'm getting is phi of t tilde plus phi dot of t tilde times delta t tilde plus phi of t tilde, and this has to be equal to phi of t tilde. And this is bar. This is bar. This is bar. And this is bar. So these two terms cancel. And what I get is that delta t tilde is equal to minus phi of t tilde and x divided by phi bar dot of t tilde. So therefore, it's crucial that phi dot on the background is non-zero. Since phi dot on the background is non-zero, such a choice of a slicing exists. I can choose this phi field to be my time. So, and that is done here. So this is this gauge choice that is done by Mehrdad. We pick phi to be constant on our time slices, and now all of the fluctuations are encoded in the metric. It shouldn't be surprising that we have the scalar fluctuations, and we have tensor fluctuations. Because we started from an action that had metric, but in addition, there was also a scalar field in it. Now, after doing this gauge fixing, which is a full fixing of the diffeomorphisms, the local diffeomorphisms to be more precise, we can plug this inside the action and derive actions for zeta and gamma. And then we can apply that procedure that we did at the beginning of the section to this zeta and gamma. So we derive some effective actions for these two variables. Let's see. I'm going to write the effective actions, but maybe here. But I'm not going to derive them. So we get an effective action for the fluctuations, which means that we plug that we plug this metric and this ansatz for the phi field inside the action, and we expand it only to second order in perturbations. Notice that we are perturbing along a solution, a background solution, which guarantees that the linear term in perturbation is going to vanish. So the quadratic term that we are going to get is the sum of two actions for free fields on this background. So I have the usual measure. So this is S2 for the fluctuations. And then there will be a part which is twice m Planck squared times epsilon times zeta dot squared minus grad zeta squared. And then we have a part for the gamma ij, which is gamma ij dot squared minus dl gamma ij dl gamma ij. Well, except that here I have 1 over a squared, and here I have 1 over a squared. So this is left as an exercise to you to derive this action from the original Einstein-Hilbert action plus S of phi when we plug these answers. But once we arrive at this point, then the problem has essentially reduced to the one that we studied before, because we effectively have this zeta is now a scalar field that lives on a de Sitter or quasi-de Sitter background. So we can apply everything that we did at the beginning of section to this zeta field. And now you see that this zeta field doesn't have any potential or any mass there. So it is indeed going to remain constant or conserved outside of the horizon. And this property of not having non-derivative interactions for zeta is true even beyond the quadratic order. But in addition to that, in addition to those scalar fluctuations, we also have the tensor fluctuations in this gamma ij. And the treatment of those is also very similar. Remember, we wrote our phi field or scalar field, we expanded it in terms of a set of modes, a set of momentum, Fourier modes, each of which would behave like a harmonic oscillator. Now, when I have a tensor field, there is little difference. The only difference is that now, in addition to expanding in terms of the Fourier modes, I should also add polarizations. So this gamma ij would be gamma ij of, just imagine, for instance, I go to the conformal time as before. Then I write this gamma ij as d3k e to the I k dot x. Now there will be a sum over two polarizations, s equals 1 and 2. So there I put the polarization vectors here, epsilon ij s, which also depend on momentum, times now gamma s k. So before there will be only one label which corresponds to the momentum. Now there will be another label which corresponds to the polarization. And now and these polarization vectors are chosen to be, of course, they are transverse and traceless just by our gauge fixing condition. So epsilon I is equal to 0, and ki epsilon ij of k is 0. But in addition, we normalize them to 1. So epsilon s prime, when I multiply them, I want them to be proportional to Kronecker delta. So once I make these choices for the polarization vectors, but these are smart choices for polarization vector. These are not random choices. I do that because when I plug them in the action, they diagonalize the action. So I get a set of decoupled modes, both in Fourier space and in polarization space. And then once I get to that point, I just have a sum over oscillators as before, and then I quantize them as we did for the scalar field. So then we are essentially done. The only difference is that now these fields that we are talking about have different normalizations. So remember, how did we choose the normalization of the fields? We use the canonical commutation relation to fix normalization. Now, if the action has a different normalization, then it will enter here. So then it's going to change the normalization and then goes through. It's kind of easy to see that if I put some normalization in my action here, let's say I put something like multiply the action by some constant alpha, then alpha would appear here, would appear here. Not here, because the canonical commutation is fixed to be this. But also here. And then here there will be alpha. Here there will be alpha. And then it will show up here as 1 over alpha. So what is the final answer? Is basically what we already have here, except for this normalization factor that we have to fix. So we get zeta of k. Oh, and there is something that, so let me do two things. One is that I don't want to keep writing this delta function of momentum conservation. So what I do is that I just explicitly insert it here. So I write zeta of k, zeta minus k, and put a prime here. Just for simplicity, so that we don't have to write this 2 pi cube delta of k1 plus k2 every time. So this prime means that I just dropped that 2 pi cube times delta 3 of k1 plus k2. So what do I get here? When I take into account this extra factor of 1 over alpha, so remember, as we said, there's a coefficient here. So if I remember correctly, then I have to get h squared over, let's see. Yeah, I think this factor of 2 is not there. Which means that my alpha here would be 2 times this, and then the answer would be 2, or would be 4 epsilon m Planck squared times k cubed. And then for gamma of S, gamma minus k of S prime, it is equal to h squared over let me check this too. And here I think it is yeah, here I think I just have this is over 8, and therefore here I get twice h squared over m Planck squared kq. Okay, it's almost the end. Maybe I can also mention another quick way of getting to this answer, which is that it's quick, but it's not as rigorous as deriving the action following the procedure, but it's actually correct. So once we derive this time, delta t, the time diffeomorphism that takes us from the slices in which phi is perturbed to the slices in which phi is not perturbed. Then we can find a relation between this curly phi and zeta by saying that zeta, remember it appears here, so it's as a correction to the scale factor. So if I have a time diffeomorphism, delta t, since the scale factor goes as e to the ht, that time diffeomorphism can be absorbed into zeta. So we can relate zeta to phi by saying that zeta is h times this delta t that we find here. So it gives us minus h phi over phi dot. Now, if we remember the fact that phi is a canonically normalized field and use the expression for the two-point function of phi, so that was just h squared over 2 k cubed. Then if I want to get from phi to zeta, I just need to multiply by the square of this factor. So that gives me h to the fourth over 2 k cubed phi dot squared. Now, we know how to relate phi dot to epsilon. What we have is that h dot is equal to 4 pi g times phi bar dot squared. Let's see, 22. So if I divide this by h squared, I will get, and there's a minus sign here, I will get minus h dot over h squared is equal to 4 pi g phi dot squared over h squared. Therefore, and this is epsilon. So therefore, we get phi bar dot squared over h squared is equal to 4 pi g is just 1 over 2 m Planck squared. So we get phi bar dot squared over h squared is twice m Planck squared times epsilon. Therefore, this is equal to h squared over 4 epsilon m Planck squared times kq, which is what we derived there. So these are some of the most remarkable predictions of inflation, which I don't have any time to discuss now. But that, I guess I'm going to talk about them in the next lecture. But this is the amazing thing. Inflation gives us these perturbations in the scalar, these scalar fluctuations that we saw are conserved outside the horizon, and therefore they are not going to be affected by whatever happens during reheating and later until they enter the horizon in the form of fluctuations in the form of adiabatic fluctuations that I think will be discussed more in other lectures in the form of fluctuations in cosmic fluids. And here we also have gravitational waves, the tensor fluctuations, which are maybe even more exciting predictions or more unique predictions of inflation, which also have some observable imprints that can, in principle, give us interesting information about the dynamics of inflation. All right. Questions? Oh. Why don't I have vector perturbations? Well, here you can just see it explicitly. There is no vector. So what are the dynamical variables that we have? There is a scalar, which is because we have this scalar field, and then there are tensors because we have the metric. In principle, in this decomposition, you see that there is a vector quantity showing up, this shift parameter, but this shift parameter is a constraint variable. So when we plug it in the action, it doesn't have any time derivative. And therefore, what we do is that we just solve for it using constraint equations and derive an effective action for the dynamical variables. But this is in a sense how we don't have vector variables. But why we don't have vector variables? I think the reason is really that we don't put it in from the beginning. There is no vector degree of freedom.
So I can say that phi is basically like creating scalar modes for the perturbations in the metric.
Uh-huh.
I can say that since it's a scalar, it cannot create vector modes.
Right. Other questions? Yes.
Understanding the surveys when they measure between this tensor to scalar ratio, is the quotient of those two things, right?
Yes.
There should be a epsilon, so to speak.
Yes.
And that is dependent on the potential that you assume for your inflating field. So by varying the potential that you assume, quadratic, power of fourth, you get a different ratio there, and that's how you test whether different potentials can have are consistent with observations or not.
Yes. Yes. Yeah, that's so. Yeah, the question was that when people talk about tensor to a scalar ratio, it's basically the ratio of these two quantities, and of course they depend on the details of the potential and everything that we use to the model that we use to describe inflation. That is, this is exactly the subject of next lecture. So I'm going to discuss in details the features of these predictions that will be then measured or observed using cosmological data and how they are constrained and how they affect the model of the inflation that we use. Is there a question here?
When you construct that variation there that you make for the field without fluctuations,
Yeah.
you wrote that metric there, like for the surfaces with that formula, but could it have other formula? Like can you obtain the field without fluctuations with other metric for HIG?
Oh, for HIJ, you mean this part? Right. So if before writing these two conditions, this expression is fully general, right? This is just another way of decomposing the variables inside metric into basically based on the transformation on the rotation subgroup. But yeah, up to here it's fully general. So your question would be probably about this. You're perhaps asking, can I choose a different condition here for fixing a spatial diffeomorphism together with the time, the condition that I chose for the time diffeomorphism, right? This is right. So we have the spatial diffeomorphisms that are fixed by this condition. Let's call it xii, and here is the time diffeomorphism that is fixed by this condition. So if the question is that can I choose a different condition for fixing xii, let's see, what is the answer? Yeah, I guess in principle you could choose a different condition. Let's see. Let's see if I can give you a different condition that is equally good. In principle, I could, for instance, say the following. This is an equally good condition, alpha times. Well, no, actually, this doesn't work because I had set the trace to 0. Yeah, I think you can make other choices, but they would be bad choices. For instance, here you could put some constant vector, vi. That, I think that would be a full gauge fixing, but not a very convenient one. But if you want to write something, or for instance, I could obviously add higher derivative terms here, like for instance equals or plus Laplacian of di gamma ij equals to 0. But yeah, I don't. Yeah, I don't know. Let me think if I can come up with something reasonable that one can do. This is a very common choice. So yeah, I'm not sure if there is another reasonable choice that one can make. I think one can make not very convenient choices. In a sense, the two conditions are not really, they don't have much to do with each other because one of them is using one of them is a condition for a spatial diffeomorphism and the other one for the time diffeomorphism. So you can imagine that you first choose your slices so that they are slices of constant phi. And then within that, you are fixing your spatial diffeomorphisms. And there, I guess you can probably make different choices. So these two gauge fixings can be done. Seems that they can be done somewhat independently. Okay. I guess it's time to stop.